Okay.
Sure.
Okay.
Can everybody see the board? Can you write something and then can we adjust the font size?
Yeah, I can. Yeah, let me see. Yeah.
If you can't see the board, then please shout out.
Okay. Okay. So I'll get started. I see the actually maybe my speed last time has ended up decreasing the audience, but anyway, because anyway it's being recorded. So even if it is in speed, you can always do the problems yourself. Stop and do that. So I'll mention about it. So last time I described teleportation. And a crucial aspect to do the teleportation was this thing, these Bell state measurements. Yeah. Okay. And now if you have interacting objects such as say for example, two electrons or something which you can bring together and make say an Ising interaction as I showed the last time they entangle, then of course you can do something like a quantum gate and you can do Bell state measurement in a certain way. Okay. For example, there's a very standard quantum circuit for doing a Bell state measurement where we do something like this thing which is called a controlled knot. Okay. And then you do Hadamard operation, okay, and that results in things becoming, say suppose we come with the state psi plus. Okay. So if you have come with such an input, okay, so this thing control knot is bit like what you can accomplish with this Ising interaction as I showed in the last class. It's with some other local gates you then convert that to this thing called control knot, which means that if this is 1 then this second one is flipped. So here this will after the C naught, okay, this will go to 0 into will be 1, okay, but then for 1 this will become 1 also, so you will get 0 plus 1 by root 2 times 1, okay. And then with that Hadamard, 0 plus 1, the Hadamard is something which takes from 0 to 0 plus 1. This is a very famous operation in quantum computing. So if you subject a plus to a Hadamard, it becomes 0, okay. If you subject a minus state, it becomes 1, okay, and vice versa, okay. So this will convert to 0, 1, okay. And in quantum computation, what we measure is always in this kind of basis, finally, it is called computational basis. So by measuring this, you can measure whether it was psi plus. When it's psi minus, it will be something else, 1, 0. So all the 4 possibilities will happen according to whether it's, yeah. But however, teleportation actually has been done instead with photons. Okay, it has not been done with. I think it has been done with atomic qubits now in a very toy situation, like but it's mainly till date. Its main way has been these kind of gates have not happened in this control knot kind of way. Okay, so you require, say for example, an atom and a photon to be able to do this kind of gates. Okay, but what it has been mainly done is with photons, and when you do with photons, then you require some interesting tricks. Okay, so maybe I will use both parts of the board. So since this is a bit like a it's a bit slight detour from the main topic of the lecture is how do you do things with non-interacting particles, okay? And you can do it when those non-interacting particles are identical so that they can show quantum indistinguishability, okay? And for that I'll show you a funny thing known in quantum optics for a long time, okay? So suppose you come with 2 photons, okay? Or two identical particles at a beam splitter, okay. So if it's coming through here, so first of all let us consider one identical particle, say let's call this path as A, okay, A and B, and goes out to C and D. Okay. We could label A is actually the same as D, B is actually the same as C, but we have just labeled this way. So suppose we are coming in with the photon in this path. For the moment, nothing is coming through the path B. Okay, then what happens? Okay, say a particle. Okay, in this mode A is like the momentum. Okay, coming into the beam splitter. Okay, so you create a particle in that. Okay, and what does the beam splitter do? If there's a reflection, okay, it's like a mirror, so it will give a I phase. Okay, so it will be I A dagger C, and if it's a continuation, then it just goes to A dagger D. Okay, and you can make it a 50-50. Okay, so this will become root 2. Okay, this is what happens. This is how the operator evolves. Okay, the state of the particle, of course, evolves. The incident state is like that, and it evolves to that. So acting on the vacuum. Okay. So the outcome is quite obvious. If a photon comes, it will go 50-50, 1 by root to the amplitude to either. Okay. Now a magic happens. This is purely quantum magic, even without interaction. So what would you expect when you come with another thing at the same time? Okay, so you come also with a dagger B acting on that 0, and then that goes to, as you see, so it will go to C as a continuation, and then it reflected by I. Okay, so that will happen if you came just with a photon in B, again 50-50. But suppose you come with the product, so each will still evolve according to that. Okay, so if you multiply those two expressions, okay, something very interesting will happen. Say these photons are not interacting at all between themselves. So how many of you already know the magic? Okay, not the learned people here. So undergraduates. So what do you expect will happen here? Will they again go all 4 possibilities are like both in one, are all 1/4 probabilities or something else? I probably wouldn't be asking you this question unless there was something magical happening. You see what is happening, you multiply these, right? Yeah. So then what will happen is that this A dagger C, A dagger D, and that one will cancel, right? This is quantum interference, and then you'll have I into A dagger C square, okay, minus A dagger D square, okay, by 2 acting on the vacuum. Okay, and what does that mean? That both particles go here or both particles go there. Okay, so this is bunching. Okay, if you came with fermionic particles, again non-interacting. Okay, electrons are a bad example. So you came with 2 neutrons. Okay, at this beam splitter, what do you think will happen? Now those terms will be 0. Okay, and the others exchanging will add up, so it will anti-bunch. Okay, so this bunching and anti-bunching. So I leave it to you to realize to see why this is a normalized state. Okay, you just have to remember harmonic oscillator algebra, and it is normalized. Okay, now how does this help in Bell state measurements even for non-interacting objects? Okay, it helps in the sense that it is done exactly using these kind of things. Okay, however, it is done not with full success, with partial success. Okay. So what happens is when you come in, okay, what was I saying? Yeah. So you come in with, say, a Bell state. So what is so we have to, so maybe one detour. So when you write a Bell state, so when you do it with photons, you do, say, for example, with polarizations. So you write H, V. Say you have a Bell, so let's write this Bell state phi plus. So in the last class I introduced phi plus, okay. where this was 0 and this was 1. So 0, 0 plus 1, 1. Okay, this can be encoded in photons in this way, right? And then what is the actually way of writing it in that second quantized notation? Okay, so it is a dagger h in some path, say let's a b, okay, and then this acts on the vacuum. Okay, so this is actually the state. Okay, this is the true state corresponding to that. Okay, with a horizontal photon in this channel A, which is coming in, another horizontal photon in channel B, which is coming in. Okay, and so this is the state phi plus. So now you can easily guess what will happen when you come with phi plus. Okay, because this H label or this V label is same in both these cases. So exactly the same algebra will happen. Okay, so things will bunch. Even if this is minus sign, things will bunch. Okay, and both will go one way. Okay, and then you put some extra things here. You put some polarization detectors here. So suppose something comes in, and then you put some kind of polarization. Now I will probably draw this very bad. Okay, I know there's an experimentalist here who does this on a daily basis. Yeah, so one of those goes to H and V will go on two separate arms. Okay, this orientation is I don't know whether it's fully correct, but anyway, you break the V and H always. Okay, and you call these detectors D1, D2. Okay, then you call this D3 and D4. Okay, and then what happens when you come with phi plus and minus is that they will either both go there, and then only one of those will click. Okay, they will either both be H or both be V. Okay, so that's the either of D1 or D2 or either yeah, so either of D1 or so either of these four will click. This will mean that it's phi plus or phi minus. Okay,
You mean D1 and D3 will click at the same time, or D2 and D4 will click at the same time?
no, so they will bunch, they will all go same way, and then they are both V or both H. So only one detector will click. Maybe that's the best way to put. Only one detector will click. Okay.
For that, should we start with A being only H and B being only V? Starting state is phi.
No, starting state is like both H or both V. Okay, in a superposition. So the scenario is very similar to this. Okay, so it's like a hidden label. Yeah, this is also H. This is also H. Okay, so it's the same math. Then they will bunch. Okay, so they will both either go there, both either go there, and then they both have the same polarization. So they will only click. One detector will click. Okay, only one.
Photons are reaching a single detector.
Yeah.
Then there's still only one click.
Yeah, only one. I mean, they are I can I cannot answer that question, but if it's a photon, generally photon number resolving is not so easy, so you probably get one click. Yeah, if you can do some kind of delay and stuff. I mean, these are really on top of each other. So one click. Okay. Then if you take psi plus. Okay, psi plus, then you see if you do this algebra with psi plus, and that's the homework, the funny thing is still you will get this bunching. Okay, this is something you probably cannot immediately think of because now this has an extra label V and H. Okay, so to do the algebra you will need to put a dagger like H here, V there, okay, and then just do the same math and you will still see that they click. this can be thought of in a easier way in a first quantized picture, but if you the maths is as easy in the second quantized picture. You just have to just have to do the math with a state which is psi plus, where psi plus will be, I can change this to psi plus, for example. Okay, psi plus will be HV plus VH. Okay, and A dagger, sorry, HA VB plus VA HB. Okay, so if you do that and just do the maths, you will again find bunching, but this time 2 of the detectors will click. So it will be D1, D2, or it will be D3, D4. Okay, so you can clearly distinguish whether you got a phi plus minus or a psi plus. Okay, and psi minus is a lot of fun. Okay, psi minus you will see will behave actually will anti-bunch like fermions. Okay, again you can just do the maths. Okay, and you will see actually minus sign is a great indication here. What was adding before will cancel now. Okay, and then you will get either D3, D2 or D1, D4, something like that. Okay. In a nutshell, you can distinguish between the so the photons are not interacting, but their quantum indistinguishability really helped you to distinguish, do this Bell state measurement, except for this thing, except for this caveat. Okay, so you can suppose you're trying to do teleportation, 1/4 probability success, 1/4 probability success. Okay, and when you get that, you have to throw away those cases. Okay, so you don't know whether it's phi plus or phi minus. Okay, yeah.
Sir, I didn't understand what do you mean by bunching of 2 photons?
Exactly this. The photons go together. Okay, or they may go together here. That's the bunching. Anti-bunching means they will go opposite. Okay, and why is this surprising? Because these are not interacting photons. It's purely happening from cancellations. Okay.
In the phi plus minus case, they will either go to D1 or D2.
Yeah. So phi plus and phi minus you cannot separately distinguish. That's a problem of doing it in this way, because we don't have interactions. Okay. But another important fact I wanted to tell you, which comes out from this way of writing the things. Okay, this comes from the when you have, so generally when we talk about system A and system B in quantum mechanics, okay, system A is say can be a superconducting qubit here, can be a superconducting qubit there. They are very different things. They are made from, they may have one atom which is different or something like that. But when you
So this is a quick confusion for psi plus. It's HV plus VH, right?
right.
So then these 2 photons are not they have a distinguishability in polarization with your flip.
That is true, but
You have to do a flip before you actually attempt making.
no, so yeah, okay, so maybe one way to think of it, that is the if you separately write the spin, the polarization part and the spatial part, right? Polarization part is symmetric, right? So
And I'm saying that if you actually don't do anything to convert both the photons to the same polarization, then you will have some probability also for the 1-1 and not just 2-0 -0, right?
no, I can do it. Yeah, it will be, yeah.
It's not 0, the probability for 1-1, because you see they are not.
No, from each term, no. But then the magic will be that they,
How will they? There is an assumption here that
Yeah.
the photons are perfectly indistinguishable.
yeah, they are indistinguishable. That's true.
Polarization label makes them
Yeah.
distinguishable.
Maybe I just do the maths and I'll find out. Okay, maybe that's good thing to do. So I did not. I was, for brevity, I was not. I was trying to avoid that maths, but let's just do it. Okay, so when we have this situation, okay, so let's do this thing. So A dagger HA, okay, we'll go to a dagger, okay. This we called C and this we call D, okay, right. So we'll go to a dagger H C, sorry, H A will go to I a dagger H C plus, okay, we'll go to a dagger H D, right. And then, so I'm not doing the normalizations now, yeah, because not, and then that will be multiplied by this a dagger VB, okay. So a dagger VB will go to a dagger VC straight plus I a dagger a dagger VC and I a dagger V D, right, okay. Now remember, this is not everything, right. So there is this extra bit, okay, which is a dagger VA and HB. So for brevity I can just shift everywhere the V and the H in these two terms, okay. So what I'll do is I'm blindly replacing H's by V's. I think hopefully that will be the right thing to, I'm not doing very, yeah, so. Is H D, okay, correct. So now you see what happens, let's see, okay. So you see there are lots of pairs of i's, so things will cancel, okay. So so let us see the terms which cancel. So I square, with I square you have HV, okay, and then this is VH, okay. So there is this cancellation from these two terms, okay. Yeah. So this also, so individual terms, of course there are other things, but because you have this sum, okay. I mean, this is usually done in a slightly different way in descriptions. They use first quantization and talk about symmetric, antisymmetric in the two parts, okay. For again, for psi minus, so I don't need to do the psi minus because you can probably see from here, okay. I leave it to, for you to work out, yeah, it's almost done here, okay. So anyway, so this is how you can do some kind of partial, Bell state measurement, okay. But what is the point I wanted to tell before moving on from this topic is that you actually, most of the time we do, when we talk about entanglement, even this Bohm's EPR spin entangled state, which Bohm introduced, like up down plus down up, you are implicitly using two labels. You really need two quantum numbers, okay. So entangled state cannot be meaningfully described if you have just one quantum number, okay. You can do that for non-identical systems, but you see you have a channel quantum number H, A or B, so it's like a momentum, okay. So you need two momentum labels to say which is which particle, because I have one photon here, one photon there, or we have one trapped ion here, one trapped ion there, okay. These are mostly identical particles, they are identical particles, right, two atoms. So you have to, so often you need two variables, and something interesting you can look up, we did some time ago, is you can exchange those labels. So you can use the polarization as the label or the moment as label, and then the other variable will be entangled. It's exactly the same how you write the thing. So when you go from this to this, you can go both the ways, right. You can write H sub A or you can write A sub H, yeah, it's completely up to you. Now, let me move on from this topic, okay. So you can do kind of Bell state measurements, okay. Now, if you have interacting particles, you can do exactly, but if you have non-interacting particles, then you have to do, with some clever technique like this. And these type of techniques are also at the heart of what people call linear optics quantum computation. So, I am not going to go there, but this kind of a flavor, okay, these kind of things. Yeah.
So if I understand correctly, this limitation of throwing away half the outcome, that is a limitation of this particular measurement setup. But if we could come up with a way, I mean, there is nothing that stops us from actually measuring in all four cases.
No, no. So it's an interesting question. Okay, so what you will need to do that kind of thing is very difficult for photons. Of course, if you can have something like say okay, yeah. So maybe this is more related to what Urvashi was asking before. Say suppose you have got this situation, right, and you have not ended up detecting the photon. Suppose you have got this situation, you have some kind of non-absorptive which way detector, you know it has gone both this way, okay. Then you can do a local rotation to convert the phi plus to a psi minus, okay, and do. So a non-absorptive which way detector can be very useful, but it's very difficult, okay. So you have to have a dispersively coupled atom, okay, whose energy will shift with single photon. That's very difficult, yeah, but yeah, okay. Now, right. So let us come back to okay. So now some kind of funny story a little bit, just building up on the teleportation that I told last time. Okay. So suppose you had, suppose you know, Alice and Bob, okay, were sharing lots of, you know, maximally entangled states, okay. I am showing one here, okay, that maybe they share lots of pairs. There are some advantages of doing that, okay. As you know, you can if you have a very perfect one, then you can do perfect teleportation. So you can, with that you can build quantum key, you can distribute a secret random key, and you can find whether someone is wanting to eavesdrop on your conversation. You can do things like that, okay. Now, Alice and Bob, and suppose Carol and David, okay, I changed these names, I used to have separate names. Anyway, so Carol and David also have this similar thing, okay. I used to use Charlie and Diana, but I think I don't use that anymore for business, okay. It's a very long time ago I first used those descriptions, okay. This is before some incidents also, yeah. So anyway, so so suppose Bob, this is the wrong way round, okay. Anyway, so suppose okay, so whatever. So suppose Alice meets David in a party, okay, and then they decided to share a lot of you know, entangled pairs among themselves, okay, so that they can secretly communicate, but they have only these halves in their pockets, so they will do a Bell state measurement here, okay. So the Bell state measurement generates a. So what happens here? So you can do the same maths as we did last time, very easy maths. You project these two, and suppose you get an outcome psi plus, okay. Suppose you share phi plus here.
They share Bell type entangled states.
Exactly, yeah. Initially,
Not arbitrary entangled.
no. Bell type entangled state, and then you do a projection here. What is your guess as to what will happen here? It will also become a psi plus instantly, okay. So they cannot prevent the other two parties immediately also getting entangled pairs, okay. Of course, they cannot in practice use it at all, right, because you remember what is important in teleportation is also to know one of these four, okay. So in some sense it's useless, but it's fun that they, you know, yeah, so, suppose they even publicly announce what outcome they got, because that's not a big problem, I guess. They still share it. but then the other parties will also have these entangled pairs. Okay. Now, this is called, so this is the first calculation I did when I started my, one of the early calculations I did in 1990, I think some point in 1997 or 1990, the paper appeared in 1990, must be 1997. And we were very excited. We have found something by which you could, you know, link things like, you know, if you shared entanglement with like a central, you know, central exchange, you can always link any pairs, yeah, by Bell state measurements and things like that. Yeah. Unfortunately, as it often happens, I mean, some of you will probably continue to do PhD, some are doing, okay, early on, and of course in 1997 it was still a novel enough result. Unfortunately, this was already known that time, and it was called entanglement swapping. Okay, so it was done already before us by Zeilinger, Horn, Eckert, and Zukowski. Okay, so then I had to do something else. So this is a typical story. So you have to do a bit more to publish. Okay, so what we did was, again, it's a fun game. It's called multi-particle entanglement swapping. Okay, so you take you can take any kinds of. So you remember the G8Z state I showed 0, 0, 0 plus 1, 1, 1. You could have that. Say take two G8Z states, and you can do again. So if you use exactly the same kind of maths I told in last class, it's very easy to do, because you just project, you take out some things, and immediately you will get to this. Yeah, the calculations are kind of trivial. Okay, and you immediately get a 4-particle entangled state and a 2-particle one. Okay, so it is fun. You can build up higher and higher entangled states just by doing these projectors. Okay. So we were able to publish multi-particle entanglement swapping. Okay.
So the referee pointed out that this was already known. How did it go?
No, multi-particle was not known. Yeah, this one we found out ourselves. Yeah. From the, no one knows, that time we got referees reports in kind of envelopes. Okay, so I think I still have it stored somewhere, and there's good reason to think that that time that kind of people still refereed. Okay, it was probably refereed by Zeilinger, I think. Yeah, he was very happy that we call this, you know, multi-particle entanglement swapping, and then we call those cat states. He was very unhappy about it. These are rightly called Greenberger Horn Zeilinger states of more and more qubits. So we changed that. Yeah.
But these pictures
Yeah.
that you're drawing,
Yeah.
can they be converted to rules in graph theory?
Maybe, yeah. Some so people. So I don't keep track. A lot of people have done a lot of things on that, but so I think earliest persons were someone in IIT Kharagpur called Pal, who was doing some graph theory. But now by now maybe a lot of things. Yeah. So the experiments were done by Chao Yang Lu much later in like mid 2000s, late 2000s. Yeah. So. Right, but you need to do, you can actually also do G8Z measurements in that way. I won't go into that yet, so it's possible. Okay. Now, these days publishing in quantum information is not that easy. Okay, it's much harder. Okay. Let us move on. So. What else is there? Right. So, okay. So now we will move on to quantifying. So what is the application of this thing like entanglement swapping? Mainly, the application is to make things like these things I drew before, quantum.
Suppose in this picture, if these two parties had some kind of entangled state with arbitrary entanglement, and these two had some other forms of entanglement, would it be possible to swap?
Yeah. I think arbitrary entanglement also. I know by now probably people have looked at lots of things, but yeah, it's what I mean. Looking at what happens. Yeah, it's so mixed states. Yeah, I mean I have never worked on that since that paper almost. Yeah, well, one or two papers we did more. I have not going into those, but otherwise we kind of stopped in that area. Okay. But yeah, I think a lot of interesting things are possible. Okay, so there is a closely related thing, measurement-based quantum computing, right? But I'm not going to cover that. But that's kind of has similarities, not a measurement-based quantum computing. They just create an arbitrary graph of qubits which are entangled in a certain way, and then do quantum Hall computation just by measurements. Okay, so there the linked entanglements do C naught, and the local measurements do like local rotations, and you can. Yeah. Okay, so one of the major applications of entanglement swapping which people tend to use is to entangle distant atoms, for example. Okay, so suppose you have atoms into different cavities. Okay. And it's very, you have distant atoms. Say these could be parts of ion traps. Okay. So linear ion traps. In ion traps, things are arranged in a line, and say you have brought a particular atom to be inside a cavity field. Okay. So then you see, what you can do is you can entangle the atom with a photon which leaks out. You can entangle the atom with a photon which leaks out, and here you do joint detections. The process which happens here is very similar to entanglement swapping, but it's slightly different in the 0-1 space, like presence-absence space. In other words, when you detect one photon here, you don't know where it came from, here or there. Okay, you entangle like ground state atom, 1 photon, excited state atom, 0 photon. Similarly here, and then when you detect 1 photon, you don't know whether it came from this or that, so it will be excited ground, ground excited. Okay, so this is an entanglement swapping like phenomena where without moving atoms physically, you can kind of create an entanglement between them. Okay.
This picture is not to suggest that the photons are arriving at the splitter at the same time.
They have to, yeah. So there is this. So this picture is very bad. Okay, so they actually. So this is one of the main challenges of this technique, that they have to be indistinguishable and they have to arrive exactly at the same time. Yeah.
How do you make sure that?
So when they do not, okay, that's a good question. So they will, this is, it's from a cavity. So when they will leak, if they do not arrive at the same time, okay, then, sorry, so 1 second. No, there are no two, sorry. I take back what I say. There are no 2 photons here. So here the Bell state is not exactly like I showed, okay. Here the state, let me write down, is E0 plus G1. Okay. And I guess what you said is there is still a problem of from the time of, but you don't know time of emission anyway. So time of detection will be something arbitrary. Here there are no 2 photons. So not like the Bell state measurement I showed. Okay, it's in a 0-1 space. Okay, so when you see when you get 1 photon, you are projecting to this E0 G1 option or G1 E0 option. Okay. Now, since you don't know the starting time when it leaks, so you just get a click. You can sometimes get 2 clicks, so that is an error. So the GG state can be there. You might get 1 click from the 1-1 component. Okay. But otherwise, and that can be again, that proportion can be reduced by reducing this. That's what they try.
Can distinguish between the 1 photon and 2 photons.
Detector, ideally that would be good, but they cannot in principle. So in practice they cannot always. So then that is kind of is not an exact Bell state. It will be like mixed with some noise.
But
okay.
Why can't the detector detect the differentiate between 1 and 2 photons? I mean, I would have thought that more electric current will be generated.
Right. Yeah, it's some detectors can. Yeah, it's a challenge. Yeah, I think people now have, again, I think Urvashi is better suited to answer this. So I think there are photon number resolving detectors these days, I guess, but it's
Still, they are not commonplace, right? So the superconducting nanowire detectors we have these, they can go down to maybe 2, but then
right,
taking it to single when differentiating from 1 and it becomes
right, right,
very
yeah.
small energy.
Yeah, so superconducting ones, and I guess they get expensive. That's the thing, but they probably can be possible. Okay.
This setup you were trying to say what exactly is the right?
Exactly. So how to entangle two distant atoms? Okay. Though atoms are massive things, they wouldn't be traveling very long distances easily. So you entangle with photons, and then you do this kind of entanglement swapping like process, but this is in the 0-1 space, absence presence space, not in horizontal vertical space. Okay. This was our work, but subsequent to our work, so this was the last work of my PhD, but subsequent to our work people have also done it in that kind of way, where you have horizontal vertical things being detected from yeah. So there you don't have this problem of imperfect fidelity. There when you detect something, you have a perfect state. Okay. Of course the problem with that is then this, that the photons have to fall at the same time and they have to be indistinguishable. Okay. So because you're using that methodology. Okay. So there are pluses and minuses. This has higher rate, but this will mix a bit of 1-1 unless you have this photon number resolution. Okay. Now so kind of long distance you want to build up this entanglement, but it is time for us to see how, I mean, essentially entanglement will essentially end up being noisy to the first approximation, and then how we can you know, get more pure entanglement out of it. Okay. And so to do that we need this process of entanglement distillation, but before jumping to something like that, it is perhaps best to do some degree of, or let me illustrate it with an example, and then we will go gradually to the quantification of entanglement. Okay. So suppose, so photons go through channels. Okay, and I will consider a simple example, simpler example here. Okay, I'll consider what is called a bit flip channel. This is purely from simplicity I am considering. This is not a realistic channel. Okay, realistic things will be involving lots of all the three possible errors that can happen. Okay, x, y, and z. So one good thing about quantum computation, you usually learn it just before quantum error correction, is that any error, I mean, for a lot of time there was a doubt whether quantum computers can at all be built, because any errors can be any unitary operation, right? But any unitary operation can always be resolved, any 2 by 2 matrix for that matter, not even need to be unitary, can be resolved in this basis of identity x, y, and z. Okay, so y is just xz. Okay, so essentially anything that happens can be thought of as either with some probability x, y, or z, but we consider just a random x error. Okay, so there is a state psi plus AB being generated. You can think of this in terms of photons being generated. Okay, so you have HV plus VH. Okay, and it goes through a channel. Only the B goes. Okay, and the channel, so A is actually held in hand in Alice's laboratory. Okay, and B is sent to Bob. So there will be identity operation acting on A, and a random bit flip XA acting on B. Okay, with some probability P. This happens with some probability P, and with some probability 1 minus P, yeah, you have nothing. So identity A cross identity B acting. Okay, so oh sorry, XB. Thanks very much. Yeah. Good, you're following. Thanks. Yeah, so it's XB. Okay. So, randomly XB happens on this the photon which is actually sent through the channel or not, with some probability p and 1 minus p nothing happens. Okay. So, you see the state which comes out ends up being a mixed state, right. How much is this area of the board accessible to people? The top, yeah, right, yeah. So anyway, I can write it here, but I think it's a lot of people are guarded. So I think maybe I try to write it here, and I'll do the maths on the whiteboard. Okay. So the state that comes out then is this kind of mixed state. Okay. So I have started using density matrices now. It will be needed like the next part of the lecture also. So so a lot of you are some of you are undergraduates, right? So you have done density matrices, right? Yeah, all of you. Yeah, yeah, that's great. Okay. So rho AB, it will become, so P, probability P, okay, times it will be the state, the original state psi plus AB, and with probability 1 minus p, it will be that it has been flipped. Okay. One of them have been flipped. So what will it become? It will become phi plus AB. Okay. Do you agree? Sorry, thanks, yeah. Wait, so very good, yeah, that's very good. You're paying very good attention, yeah. So okay, psi plus, okay. So you have this kind of state coming out, and this, as you know, this is actually not very good for teleportation, because you see teleportation had those other local operations you have to do, and they will be different for those two states. Okay. So we kind of want to bring it to either that or this. We have to bring it to either of those. So how can we do that? We can increase the concentration of one of those to other if we can make these probabilities ratios squared. Okay. Each time you square it, you concentrate on one or the other. Okay. And this is a step-by-step upgrade you can do, but you need two pairs. Okay. So this is called entanglement distillation. It is being exemplified here really by a toy problem, but you will see it's quite instructive. Is the easiest one to do. I cannot do the real one. Okay. It's on the board. It's difficult. Okay. So right. So we have this. We now take two pairs. Okay. So what is the situation with two pairs with probability p square? Okay. You have two phi pluses. So you have a phi plus a1 b1. You have a phi plus a2 b2. Okay. That's one of the options. So we will do all the four options. Okay. And what is the circuit we are going to do on them? Okay. The circuit has to be done is that this is the shared thing. Okay. What has to be done is called a bilateral C naught. Okay. So this is one shared pair A1 B1. This is the other shared pair A2 B2. You have to do a bilateral C naught, and then you have to detect the second pair. Okay. And you retain coincidence. When they are both 1 or both 0, okay, that measurement outcome, then you retain the first pair. Okay, so you take two pairs, so you have done two transmissions. So first one is called A1 B1, the second one is called A2B2. Okay. So, you have done 2 transmissions from Alice to Bob. Okay. This is Alice's side, I think the black one is better.
So when these pictures have been drawn, we imagine that they are being transmitted at the same time.
Yeah, they have been transmitted first. A lot of them have been transmitted first, okay, in parallel, okay, and or in sequence with a quantum memory. I mean, that is difficult in practice, but you keep them, you retain them after they have been transmitted. And actually, the picture is that several pairs have been transmitted, and so this is with Alice, this is with Bob. Okay, and then you upgrade it by some local actions. These local actions will be a control knot between A1 and A2 qubit. So, those held by Alice among the pairs she has, those held by Bob among the pairs he has. Okay, the control knot, and then there is a measurement. And now let us write this explicitly down. Oh, this is breaking. Actually, I can probably say this in words as well. It's okay. Maybe I write one, and then it will become very clear to you the other ones. Okay. Sorry. Okay, this is the state that is being shared with A1, A2 with Alice. And B1, B2 with Bob. Okay. Now, this bilateral C naught will be C naught based on this to this, and this to this. Okay. So, you see both are same. So, both will be flipped or both will not be flipped in the target. This is the target. This is the target of that C naught. We call the one on which it is controlled is the one which is controlled. Whether it's 0, nothing happens. When it's 1, something happens. Okay. That is called the control. This is called the target. So, this is the control. Control are both the same. So, targets are both the same. Targets would both be flipped or not flipped, right. So, the outcome after this bilateral C naught, we call it BC naught for example, will just be again phi plus A1 B1 phi plus A2 B2. Okay. So, if you measure you will measure coincidence and retain with p square, you will retain phi plus. So, with p square amplitude you will retain the phi plus. Now, this phi plus will be between A1 B1. Okay. Now, consider the other cases when you have phi plus psi plus with p1 minus p probability. Psi plus is mismatched and these are both flipping. So, again you will not have coincidence, you will have psi plus, right. So, you will throw that away. When you have psi plus phi plus, one will flip, the other will not flip. So, again you will not have coincidence, you will throw that away. But when you have psi plus it is interesting. Okay. So, psi plus are 0 1 and 1 0, but this is also 0 1 and 1 0. So, one of them will flip, become 0 0, the other will not flip. Okay. So, again you will have coincidence for that case when both are. So, you will get 1 minus p whole square, okay, psi plus A1 B1. Okay. This is not normalized, so you have to renormalize the state by dividing by the sum. Okay. But you see, it is like if you started with a state which is like 2/3 and 1/3, right? You already got the ratio now to be 4/9 to 1/9 to Yeah, 1/9 to rest. Yeah, you have to normalize. Anyway, so you amplify the ratio of the probabilities, right? Now you have to do it step by step. Okay, it can be shown that the yield is finite. Yeah, you might wonder whether the yield vanishes because you have to throw away so much. Okay, but the yield is also finite. Okay, and essentially what you can do in arbitrary distillation is a formula in terms of entropies. I think I probably, because of time, I have to leave I have to introduce von Neumann entropy to you to show this asymptotic yield here. Okay, in general. Okay, only some things are known, very less is known, but we can show that. So in the, I think time wise, how am I doing now? It is it's 5 to 4, right? So maybe I do a bit more progress, and then I do I do 10 more minutes, then
Yeah,
4 5, yeah, part at 4, right, correct. So what else can I don't think I can do much more without doing some entanglement measures, but let me just introduce longer lecture. Okay. So maybe I just end up by drawing a picture here of the schematics, that so that you have an idea why we are doing these things. Okay. So what is the picture here? So that you transmit many and then they end up like dotted entangled things. Dotted means that they end up with kind of a row AB, which is kind of very noisy. Okay. Then you do these kinds of operations that I said. Okay, you do pairwise dot, then you go one more step, okay, from that and that, like that. Okay, and eventually you end up with an yield. A finite yield is very important of this nearly, you can go to 99%, 99.99%, whatever, in a very few steps, and then you end up with something like that, and rest useless. Okay, rest I am not drawing any dots between. Okay, this is called entanglement distillation. And this is what makes teleportation a very practically useful procedure, because once you have entanglement distillation, you can send perfect quantum states by teleportation. Okay, so teleportation is the ideal thing to link different quantum registers and things only when you do this procedure of entanglement distillation. Okay, and that can be used to define things like distillable entanglement. Then maybe that I speak about in the early part of next lecture. So next lecture, first 20 minutes to half an hour maybe on entanglement, and then I'll start quantum computation. But there is slightly more to it. What people do is also they use entanglement swapping after that. So suppose there's a distance your photon goes before getting absorbed or getting too corrupted. Then you do this entanglement distillation, create perfect ones, and then they link by entanglement swapping. Okay, this is called entanglement. This is called quantum repeaters. Okay. So this was actually, unfortunately, we could have done this, but the idea didn't click to us despite doing some of the precursor things. But so it was done by Briegel and Zoller and others. But it's a very I think people still, to my understanding, people still don't use so much in photonic communication. But I think in the next stage people will start using quantum repeaters. Okay? But you see, you needed these C naughts and stuff. So you kind of need to probably have something which does a good C naught, which means you need a light atom system or atom light system. So there are some catches there. Yeah. So I'll stop at this moment, and then we'll go to von Neumann entropy and things in the next lecture. Thank you.
So we continue here.
Yeah. Okay. Monday. Okay.